Chapter 2. Shaping of the Earth's Surface. Understanding Society, India and Beyond. Grade 9, Part 1. This teaching version breaks the entire chapter, main text, figures, boxes, let's explore, don't miss out, think about it, and end questions.
The big questions of this chapter. 1. What shapes the Earth's surface? 2. What is plate tectonics? What are the effects of plate movement? 3. How are landforms formed and how are they classified? 4. How are humans and other living beings connected to these landforms? 5. How do disasters associated with different landforms impact human lives?
Introduction and the big picture. The Earth's surface is always changing. The Earth's surface is not fixed. It is constantly transformed. Powerful forces act from within the planet and on the surface, slowly reshaping the land over time. The Earth looks permanent within a human lifetime, but over thousands and millions of years, its surface is completely remade. Two kinds of energy drive this: internal, endogenic energy from the hot interior, and external, exogenic energy from the sun, water, wind, and ice acting at the surface. Because most of these changes are extremely slow, we rarely notice them, except during sudden events like earthquakes, volcanic eruptions, or landslides.
Two sets of forces: internal, inside, and external, surface forces shape the land. Internal forces build up features. External forces wear them down. Together, they create all landforms. Internal, endogenic forces come from deep inside the Earth and are mostly constructive. They raise mountains, build volcanoes, and open ocean basins. External, exogenic forces work at the surface and are mostly destructive. Weathering, erosion, and deposition slowly wear high land down and fill up low areas. Every landform is the result of a constant tug-of-war between these building up and wearing down forces.
Plate tectonics is the key idea. Plate tectonics explains many surface changes. It describes how large pieces of the Earth's crust move slowly over the molten mantle, giving rise to mountains, volcanoes, plains, and valleys. Plate tectonics is the single big theory that ties this whole chapter together. It says the Earth's rigid outer shell is cracked into moving plates that float on the softer, partly molten layer below. Where these plates push together, pull apart, or slide past one another, we get mountains, volcanoes, rift valleys, and earthquakes. So one idea, moving plates, explains features found all over the world.
Why understanding this matters? It helps explain natural phenomena. Plate tectonics plus landforms explain earthquakes, volcanic eruptions, and the formation of continents and oceans, helping us appreciate the dynamic Earth. Before this theory, people could not explain why earthquakes and volcanoes occur in belts, or how continents and oceans came to be. Plate tectonics answers these puzzles by linking plate boundaries to earthquake and volcano zones, and by showing how continents drifted to their present positions. It also has a practical value. It helps scientists identify high-risk regions and prepare for disasters.
What is a landform? A landform is a natural feature on the Earth's surface. It is formed by processes like weathering, erosion, deposition, and crustal movement. A landform is any natural shape on the Earth's surface. It is never built by humans. Landforms are produced by a mix of internal movement, which lifts or lowers land, and external processes: weathering, breaking rock; erosion, wearing and carrying it away; and deposition, dropping it elsewhere. Mountains, valleys, plateaus, plains, deserts, and coasts are all landforms sculpted over very long periods. In-depth. Examples of landforms include mountains, valleys, plateaus, plains, deserts, and coastal features. The Earth's interior. Plate tectonics, the theory. Plate tectonics was given by W.J. Morgan. It is an important theory in earth science that explains the movement of the Earth's crust. The theory of plate tectonics was proposed by W.J. Morgan. It is one of the most important ideas in earth science because it explains, in a single framework, how and why the crust moves. For exams, remember the name Morgan, and remember that the theory is specifically about the movement of the Earth's crust.
The crust is broken into plates.
The outermost layer is not one single piece. It is broken into several large and small pieces called tectonic plates, which move slowly over the semi-molten layer beneath and cause mountains, earthquakes, and volcanoes. Earlier people imagined the crust as one continuous solid shell, but it is really broken into several large and small tectonic plates, like the cracked pieces of an eggshell. These plates rest on and drift over the semi-molten layer beneath them. Their slow movement is directly responsible for building mountains and for triggering earthquakes and volcanic eruptions. 3 main layers of the Earth. The Earth is made of crust, mantle, and core. The crust is outermost. We live on it. The mantle is very thick and hot below it, and the core is the innermost, extremely hot and heavy layer. The Earth is layered like an onion. The crust is the thin, solid outer skin we live on. The mantle below it is very thick, hot, and mostly solid. And the core at the center is extremely hot and heavy. Each layer differs in thickness, temperature, and the material it is made of, and together they control what happens at the surface.
The crust.
The crust is the thin outer layer. Its thickness varies, about 30 to 40 kilometers under continents, and only 5 to 7 kilometers under the ocean. The crust is surprisingly thin compared with the size of the planet. It is thicker, about 30 to 40 kilometers, under the continents, and much thinner, only about 5 to 7 kilometers, beneath the oceans. This is why we separate continental crust from oceanic crust, a difference that matters when an oceanic and a continental plate collide. The mantle. The mantle lies between crust and outer core. It is the mostly solid layer, very thick, about 2,900 kilometers, and hot. The mantle sits between the crust and the outer core, and is the thickest layer, about 2,900 kilometers deep. It is mostly solid rock, but so hot that its upper part can flow very slowly. Heat moving through the mantle drives the convection currents that make the plates move.
Lithosphere and Asthenosphere.
These 2 layers control plate movement. The lithosphere equals crust plus upper mantle, rigid outer layer, approximately 100 kilometers. Below it lies the asthenosphere, a hot, semi-molten, mobile layer, approximately 200 kilometers, that allows plates to move. These 2 layers explain how plates move. The lithosphere is the rigid outer part. Crust plus uppermost mantle, about 100 kilometers thick, and it is what cracks into plates. Just below it lies the asthenosphere, about 200 kilometers thick, a hot, partly molten, mobile layer. Because the asthenosphere can flow slowly, the rigid plates resting on it are able to slide and drift. Outer core and inner core. The core has 2 parts. The outer core is a fluid layer mainly of iron and nickel, approximately 2,200 kilometers. The inner core is a solid, hot, spinning metal ball, the densest part of the Earth, approximately 1,250 kilometers. The core has 2 parts. The outer core is liquid, fluid, made mainly of iron and nickel, about 2,200 kilometers thick, and its movement is linked to the Earth's magnetic field. The inner core is solid, even though it is the hottest part. The enormous pressure keeps it solid. It is a dense, spinning metal ball about 1,250 kilometers in radius, and the densest part of the Earth. In depth, total radius shown is about 6,375 kilometers. Oceanic crust approximately 5 kilometers. Continental crust approximately 30 kilometers.
Tectonic plates and plate boundaries. What tectonic plates are? Plates are massive slabs of solid rock. They move very slowly, usually a few centimeters per year. Tectonic plates are enormous, thick slabs of solid rock that make up the lithosphere. Although they are massive, they move extremely slowly, only a few centimeters each year, roughly the speed at which your fingernails grow. Over millions of years, even this tiny motion adds up to continents drifting thousands of kilometers.
3 types of tectonic plates. Plates are continental, oceanic, or mixed. Continental plates carry continents, oceanic plates carry ocean floors, and mixed plates carry both continents and oceans. Plates are classified by what they carry. Continental plates carry land masses, oceanic plates carry the ocean floor, and mixed plates carry both. This matters at boundaries because oceanic crust is denser and thinner than continental crust, so the two behave very differently when plates collide.
Major tectonic plates of the world. There are several major plates: Pacific, Eurasian, African, North American, South American, Indo-Australian, and Antarctic plates. The Earth's surface is made of several major plates plus many smaller minor ones. The 7 big plates are the Pacific, Eurasian, African, North American, South American, Indo-Australian, and Antarctic. India sits on the Indo-Australian plate, whose northward push into the Eurasian plate raised and is still raising the Himalayas.
What makes plates move? Convection currents in the mantle move the plates. Heat from the core makes molten mantle material rise while cooler material sinks. This continuous cycle pushes and pulls the plates in different directions. Plates move because of convection currents in the hot mantle. Heat from the core warms the lower mantle, making that material rise. As it nears the surface, it cools and sinks again, forming huge circular loops. These currents act like a slow-moving conveyor belt, dragging and pushing the plates riding above them in different directions.
Plate boundaries. Edges where plates meet are called plate boundaries. There are 3 main types: convergent, divergent, and transform. The zones where 2 plates meet are called plate boundaries, and this is where most of the action happens: mountains, volcanoes, and earthquakes. There are 3 main types depending on how the plates move relative to each other: convergent, coming together; divergent, moving apart; and transform, sliding past.
Convergent boundary. Continent plus continent. 2 plates move towards each other. When continental plates collide, they push up fold mountains such as the Himalaya. At a convergent boundary, the plates push towards each other. When 2 continental plates collide, neither sinks easily, so the crust between them crumples and is pushed upward into fold mountains. The Himalayas are the classic example, formed by the Indian plate colliding with the Eurasian plate, and they are still rising today.
One convergent boundary: ocean plus continent. The oceanic plate sinks under the continental plate. This subduction leads to volcanic activity and earthquakes. When an oceanic plate meets a continental plate, the denser oceanic plate bends and sinks beneath the lighter continental plate, a process called subduction. As the sinking plate descends into the hot mantle, it melts, and this magma rises to form volcanoes, while the grinding between the plates triggers powerful earthquakes.
Divergent boundary. Plates move away from each other. Magma rises from below and forms new crust, creating mid-ocean ridges. For example, the Mid-Atlantic Ridge. At a divergent boundary, two plates move away from each other, opening a gap. Magma rises to fill that gap and cools to form brand new crust, building underwater mountain chains called mid-ocean ridges. The Mid-Atlantic Ridge is the best known example where the Atlantic Ocean is slowly getting wider.
Transform boundary. Plates slide past each other. No crust is created or destroyed, but this movement mainly causes earthquakes. For example, the San Andreas Fault in the USA. At a transform boundary, the plates neither collide nor separate. They slide horizontally past each other. Since no crust is made or destroyed, no mountains or volcanoes form, but the plates often get locked, build up stress, and then suddenly slip, causing strong earthquakes. The San Andreas Fault in California is the famous example. Role of plate tectonics in shaping the surface. Plate movement builds major features. It leads to mountains, valleys, ocean basins, volcanoes, and earthquakes, and explains the distribution of continents and oceans. Plate tectonics is the master process shaping the Earth's surface on a large scale. Plate movements create mountains, valleys, ocean basins, volcanoes, and earthquakes. And over millions of years, they have arranged where the continents and oceans lie. In short, the world map we know today is a product of moving plates.
The Ring of Fire. Most earthquakes and volcanoes occur along plate boundaries. They cluster around the Pacific Ocean in a zone called the Ring of Fire. Because earthquakes and volcanoes are caused by plate movement, they are concentrated along plate boundaries rather than spread out evenly. A large number of active boundaries encircle the Pacific Ocean, forming a horseshoe-shaped belt of intense volcanic and earthquake activity known as the Ring of Fire.
Let's explore plates versus disasters. Compare the plate map, figure 2.3, with the earthquake volcano map, figure 2.4. You will notice earthquakes and volcanoes line up along plate boundaries, showing a strong correlation. This activity asks you to place the plate map, figure 2.3, beside the earthquake and volcano map, figure 2.4. When you do, the dots marking earthquakes and volcanoes trace out the plate boundaries almost exactly. This close match is direct evidence that plate boundaries are the source of these events. In depth, let's map activity. Pick any two plates and note their continents and oceans in a table.
Conclusion on plate tectonics. The theory explains a changing Earth. It explains the origin of many landforms and disasters and helps identify earthquake and volcano-prone regions for disaster management. To sum up, plate tectonics gives us a single, powerful explanation for a constantly changing Earth. It accounts for the origin of many landforms and natural disasters. Its practical value is that by mapping plate boundaries, we can identify earthquake and volcano-prone regions in advance and draw up disaster management plans that save lives.